Hi, my name's Andrew. I'll be giving you a rundown of my calculations of significance for topics 5 through 12. So in my first problem, I look at the internal flow and friction loss, pump analysis, and flow through porous media of a water supply to a fountain. Basically, this system has two pumps running in parallel, which pump water to this fountain. Along the way, there are friction losses associated with the lengths of these pipes, as well as the bends and turns they take. This is the first part of the problem. The second part of the problem deals with this filtration through porous media over here, and so we'll get to that. So this first part of the problem, we use the net positive suction head as well as the superficial velocity to determine the flow rate of the pumps in parallel. After this is done, we can determine the frictional loss due to the lengths of these pipes by using the frictional loss equation for laminar circular pipes. Once this is done, the frictional loss for the bends in the pipes is found next. And so these frictional losses are combined, and therefore we can find our frictional head loss. The next part of the question asks us to draw a pump diagram for this system. Basically, there's a pump performance curve and a system curve, as well as net positive suction head required and available. And these are displayed on our graph right here. When you go from one pump to two pumps in parallel, the flow rates are actually additive, and so the curve will extend to double the length in the Q axis. So for part two of this problem, we're dealing with we're trying to find the viscosity of the dirty fountain water, which is being filtered out of this system. To do this, we're going to assume laminar flow and uniform particle size. Basically, from a Bernoulli analysis, we can find that the change in potential energy is equal to the frictional loss factor of the bed. Using the Ergun equation, we can put this frictional loss factor into terms we know from the givens in this equation in this problem. Then we can determine the superficial velocity and then the viscosity pretty easily. And then my next problem is a SpaceX materials test. Basically, the engineers at SpaceX are testing new nose cone materials on this sphere right here. They send a supersonic rocket up into space and drop this ball from there. So there's, again, two parts to this problem, the external flow part and the compressible flow part. The compressible flow part deals with this rocket thruster right here, and the external flow part deals with the terminal velocity of this falling ball. The compressible flow bit, we're trying to find the ratio between the exit and the throat areas. This is an equation we are actually given in the handout, but we don't have some of the terms here, so we need to solve for the Mach number by dividing the velocity by the speed of sound. So we find the speed of sound, and we can do that, find our Mach number, then we can find our ratio between these two areas. After this is done, we can depict this rocket thruster and categorize it appropriately as subsonic over here, sonic in the throat, and supersonic at the exit. For part two of this problem, we're trying to find the terminal velocity of that falling sphere. Again, we have a terminal velocity equation, yet we're missing some of the terms here. So what we're going to do is we're going to find this coefficient of drag from the Reynolds number, which we were given, and the coefficient is found to be 0.44. This we can then use to determine the terminal velocity, which is 998 meters per second. My next problem deals with a wave's underbelly flow. This is a Navier-Stokes equation in which we're going to be looking at the microscopic mass balance, momentum balance, no-slip boundary condition, and analytical Navier-Stokes solution. In this, we're going to, I was actually pretty inspired by this photo. I saw these remora swimming within the velocity profile of this big whale, and I thought that was pretty interesting. So basically in this problem, we're trying to find this velocity profile, which the fish would swim in. To do this, we first take our continuity equation and apply all of our assumptions, and then we can find that the dvx dx is equal to 0. This will help us later in the x momentum balance, where we can use this continuity twice to produce, along with our other assumptions, to produce this second order derivative, which we can then integrate twice and then find these constants of integrations using our boundary conditions, which are both no slip conditions at the floor and at the whale. Our velocity profile ends up being 1.5 y. The question was asked, why is the flow faster near the whale, and explain the development of the velocity profile. So the flow is faster at the whale due to the no slip condition, and this makes it so the fluid at the whale is the speed of the whale, and this drags additional streamlines to develop a velocity profile over time. As the boundary layer develops, the velocity profile will become more linear, and this relationship will become more linear. The next problem deals with easy cheese extrusion. We're going to look at another Navier-Stokes equation in which we're using the microscopic mass and momentum balances, as well as taking a look at where a no-flux symmetry boundary condition could be applied, in addition to a numerical Navier-Stokes solution. In this problem, easy cheese is extruded through the tip of the aerosol can, and we are given some information about this, and we are asked to find the velocity profile. And so to do this, we're actually going to take a look at the continuity equation and x momentum balances again, and find this second order differential equation, which we can then plug into the second order finite differencing formula, and then solve for Vx of n. So this is the velocity at any node within the flow, and this is dependent on the nodes around it. From here, it's an Excel problem, and so I asked for the Excel procedure. Basically, we're going to enable circular references so that Excel can do this calculation. Then we're going to, then we're going to apply the boundary conditions at x of Vx of n equals 0 and n equals the final n. And these are both the nodes at the walls, which we can use the boundary conditions for, the no-slip boundary conditions for. So these velocities are 0, and these can be manually inputted. And to compare this problem to an analytical solution would have used a symmetrical or no-flux boundary condition, which can be applied after the first integration, given that the flow is fully developed and exactly symmetrical. And du of x dy equals 0 is valid at this point because of the symmetry. There's no flux to either side. From here, another integration can be performed, and the no-slip boundary condition can also be applied at one of the walls to find the other integration constant. Causes an error in this calculation that we did could be due to the assumptions we use, such as a fully developed flow for an aerosol can, as well as Newtonian properties. These are not necessarily, skip it again. these are not necessarily true in the real world, and that these can lead to error. Additionally, error can result from the accuracy of the finite differencing used, and this is due to the difference between the distance between the nodes. This is not a continuous equation like the analytical solution. So that is it. Thank you very much.